This last bit is about something we talked about in the last chapter, diffusion and effusion, and the rate at which that occurs for different gases. Different gases will diffuse and effuse at different rates because of their difference in sizes. I'll probably throw up a video again to help you kind of visualize that. All right, but you do need to know the definitions of these. We've already talked about them. Make sure you know that diffusion is the property of gases, that if you let a sample of gas go into a large room, that sample of gas will move until it fills the room with the gas. And that's called diffusion. Effusion has to do with fluids being able to go through a small opening in a container. All right, tiny opening. Okay. So, and remember from last chapter that A and B, diffusion and effusion, happens because of that kinetic molecular theory, because of the kinetic energy of gas molecules. All right. And recall what kinetic energy is. Well, kinetic energy is 1/2 mass times velocity squared. So kinetic energy is totally dependent on the mass of the gas and the velocity of the gas. What this allows us to do is predict masses of gases, according to how fast they are traveling. So how fast they effuse, okay? So that's what Graham came up with in his law, was all based on this kinetic energy equation here. And what he stated was this, that the rates of effusion, again at the same conditions of temperature and pressure, are inversely proportional to the square roots of the gases' molar masses. Kind of cool, gases' molar masses. Okay, so in math terms, here is the math terms. So the rate of effusion of A over the rate of effusion of B is going to be equal to the molar mass of B, the square root of that, divided by the molar mass of A, the square root of that. Okay, so what does this mean? Let's try a little problem, okay? So we are supposed to compare the rates of effusion of hydrogen and oxygen. So we're trying to find this, trying to find the ratio of the rate of effusion, and we know that we're going to plug it into that. So rate of effusion of A, our first gas is hydrogen. Rate of effusion of B, our second gas is oxygen, is going to be equal to the square root of the molar mass of B. Okay, so rate of our first gas is hydrogen. Remember, hydrogen is diatomic. So what's this ratio? Rate of oxygen is going to be equal to the square root of the molar mass of B. What's gas B? Well, it's oxygen. What is the molar mass of gas B? Well, oxygen has an average atomic mass of 16, but oxygen gas is 2 of those put together. So the molar mass of oxygen is 32. Divided by the square root of the molar mass of A. So what is the molar mass of hydrogen gas? Well, hydrogen has an average atomic mass of 1, but it's diatomic. So that is square root of 2. Alrighty, so just using our simplification of radicals, we know that we can just divide these two. What we end up with is this is going to be equal to the square root of 32 divided by 2, which is the square root of 16, which is 4. Alright, so what this is saying is that the rate of effusion of hydrogen gas will be 4 times faster than the rate of effusion of oxygen gas. And that's all based on the fact that these gases have different masses, right? And that's the way that works. And that is what you need to know for your semester final.